Um, okay, so hi everybody. So it's lecture 25. Uh, and a couple of things. So one is that homework 12 is postponed to next week. So the homework that was assigned last week is now due next week. And the reason is it actually, in retrospect, it was probably too hard given only one lecture of graph theory. So I think you'll be better prepared to do it after today's lecture. And then the other thing is that we're not really using the textbook for graph theory. I don't really like the way it's organized. And so many students have told me that they're feeling kind of a little bit lost. And so what I've done is I'm going to type up these lecture notes for graph theory. So I've started typing them up, and there'll be a link to this on B courses. So you can just use this instead of the textbook. So this is a concise notes that has all the definitions that you need, and it will also have all the theorems that we prove. So importantly, you can just focus on understanding the lecture because of this, and use this as a reading. And then finally, I realized that we never did regrades for midterm 2, so we will do that. Just not right now because it's Thanksgiving and the GSIs are on break, so we'll do regrades after the break. Okay. So this is the, I guess, second or third lecture on graph theory. And I want to cover 3 things in this lecture. So one is I want to talk about subgraphs of a graph. Then I'm going to talk about a specific class of graphs that are very important and arise as subgraphs, which are trees. And then finally, I'm going to talk about K coloring a graph. So last time we talked about 2 coloring, and now we're going to talk about a generalization of that to more than 2 colors. So that's the plan for today's lecture. So let me start by talking about subgraphs. So far, we've just looked at one graph at a time, right? So if you have a graph, then it's just a set of vertices and a set of edges. And we're now going to talk about, pairs of graphs. And one important way that a pair of graphs can be related is by one being a subgraph of the other. So a graph H, let's say with vertex set W and edge set F, is a subgraph of a graph G with vertex set V and edge set E if the natural thing is true. If the vertex set of H is a subset of the vertex set of V, and if the edge set of H is a subset of the edge set of V. So it's not a surprising definition. So for example, okay, I'm just going to draw some pictures. Here's a graph, G, and this has a lot of different subgraphs. So any graph that you get by deleting some of the edges and keeping the vertices is a subgraph. Or you could even delete some of the vertices. This is also a subgraph. So of course these are labeled 1, 2, 3, 4. Or you could just look at the graph with the same set of vertices, but none of the edges. So here are some. This is just some. These are some of the different types of subgraphs of this given graph. So let's call them H1, H2, H3, H4. So this example shows that there are a few standard ways to create subgraphs of a given graph that come up a lot. So here are some common ways to produce subgraphs. So the most common way maybe is just to delete a vertex and all of the edges incident to that vertex. So delete a vertex and all edges incident with it. So specifically, if G is a graph, then if X is a vertex in G, then you can take a subgraph H to be the graph with vertex set V with this X removed, and edge set all the edges in E except those that don't include X. So E doesn't include X. Okay, so this is what you get by deleting a vertex. So for example, in this case, in the stuff I drew above, which of the graphs is an example of a vertex deletion?
Only H2, right?
Only H2. Yeah. Exactly, because in H2, I've deleted the vertex. Sorry, this is a mistake. I shouldn't have renumbered this. This is 2, right? In H2, I deleted the vertex 1, right? I deleted the vertex 1 and all of its neighbors. So an example of this would be H2. Okay, so that's one way. Another way is to delete an edge. This is actually in some ways simpler. It's saying don't change the vertex set, just delete an edge. So this means if you have an edge in the edge set of G, then you take H to be the graph with the same vertex set, and the edge set is just E minus this edge E. So in the above examples, what's an example of this kind of construction?
H1, and then repeating that operation, you eventually get to H4.
Yeah.
Sorry.
Oh, sorry. Yeah, there are only 3 graphs.
Reading H3.
No, I'm sorry. There are only 3 graphs here. So cool. I don't know why I wrote H4. So there are only 3 graphs here. Yeah. So good point. So example of this is H1, and also H3 if you do it 4 times, right? If you delete all 4 edges. So H3 is if you, I don't know what this, okay, I don't know what symbol I'm using here, but if you do this 4 times, then you get H3. Okay. Good. So those are the 2 principal ways to get a subgraph. And there's one special case which is going to come up a lot, which is if you don't change the vertex set, it's called a spanning subgraph. So if W equals V, then H is called a spanning subgraph. So in the examples above, which ones are spanning subgraphs?
All except H2.
Yeah, H1 and H3, because they have the same set of vertices, except in H2, I deleted a vertex. Okay, so this is a very common way to come up with subgraphs of a given graph. And we're going to use this in a bunch of proofs coming up. Okay, So now, so by the way, just out of curiosity, I mean, just to make sure we understand this concept, if a graph G has M edges, how many spanning subgraphs does it have? So any thoughts on this?
Wait, doesn't it depend more on the vertices than the edges?
Well, let's think about this. So spanning subgraph means you keep the set of vertices the same.
Oh wait, you just like remove some number of edges, so that would be like 2 to the mth power, I think.
Exactly, yeah. Every spanning subgraph is uniquely defined by choosing a subset of the edges of G. So the answer to this question is 2 to the m, corresponding to the power set of the edge set of G. Okay, good. So let's now use this to do something interesting. Let's talk about trees. Trees are like one of my favorite classes of graphs. Okay, so what's the definition of a tree? We need one definition. So there's a very important type of subgraph that comes up a lot in graph theory, and that's a cycle. Okay, so a cycle graph I defined last time, but yeah, a cycle is a simple circuit. Okay, so it's a circuit, so it's a path from some vertex to itself in which no edges are repeated. Okay, and a graph is acyclic if it does not contain a cycle. As a subgraph. Okay, so in these examples above, which of these are acyclic?
All except for G.
Yeah, so G is not acyclic because G is actually a cycle itself. But the rest of them don't contain a cycle as a subgraph, so they're acyclic. Okay, so here's a definition. A tree is a connected acyclic graph.
Should a tree also be simple? Or can you have non-simple trees?
Yeah, well, okay, so a tree has to be simple because if I have a double edge, that's actually a cycle, right?
Cool. Thank you.
It's already a cycle. So this is so yeah. So we can assume the graph is simple. So tree is a connected acyclic graph. So these are the two defining properties of trees. They're connected and they're acyclic. So going back to the graphs above, which of these are trees?
H1 and H2.
H1 and H2, because they're connected and they don't have a cycle. Okay, so H1 and H2 above are trees. The rest are not trees for different reasons, right? G is not a tree because it has a cycle, and H3 is not a tree because it's not connected. Okay, so trees, look like they look like trees. Okay. That's why they're called trees. And what we're going to do here is we're going to prove some basic fundamental properties of trees. And then we're going to show how they're related to general graphs being connected. So first, I'm going to give you an alternate characterization of trees. So here's a theorem. A graph G is a tree if and only if every pair of distinct vertices in G is connected by a unique path. Okay, so in this example that's over here, you'll notice, sorry, by a unique simple path. So you'll notice in this example, if I take any pair of vertices, there's only one way to get between them. Now, why is the word simple needed here? Can anybody see, would it be true if I remove the word simple?
If you didn't have simple, you could like double back on yourself and create extra
You
roots.
need the word simple because if you're allowed to repeat edges, then you could go from X to Y and then you could just, go here and go here again or something, then it wouldn't be unique. You could add some loops like that. So let's prove this. So simple path means this is not allowed. Oh, sorry, Y is still there. So this is if and only if, right? So this has two directions. And so let's prove the forward direction. So for the forward direction, it's going to be easier to prove the contrapositive. So I'm going to prove that if there's a pair of vertices that does not have a unique simple path, then the graph's not a tree. Okay. So contrapositive means you assume that there's some pair of distinct vertices that's not connected by a unique path. Okay, so assume X and Y are vertices in G such that well, there are two possibilities. If there's not a unique path, then there are either zero paths or there are two paths, right? Such that X and Y are not connected by a unique simple path. Okay. Well, so case one is that they're not connected by any path. Well, in this case, I claim we're done. Why?
And G isn't connected.
Yeah, G isn't connected, right? So a tree has to be connected. So then G is not connected. And so it's not a tree. Case two is more interesting. Case two is that they're connected by two paths. There are two distinct simple paths. Now let's give them names. It's always good to give things names. So there are these two vertices, x and y, and now they're two distinct paths, right? So let's give them names. Let's call the first one v. So x is v naught, v1, v2, dot, 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 all the way up to v, let's say m, which is y. And then there's another one where x is w naught, w1. And they don't have to have the same length, by the way. They could have different lengths. So this is some wl equals y. And so the picture associated with this is that there's a vertex x here. There's a vertex y here. And now I have these two different simple paths. So this is the first path. Let's call this path pi1. And let's call this pi2. And they don't have to have the same length, right? So this one could be longer, let's say. And now these paths really are a sequence, right? Paths are ordered. And so in the picture, sometimes it's helpful to draw, even though the graph is undirected, it's helpful to draw some arrows to show where the path is going. So that's pi1, and this is pi2.
I have a question.
Yep.
Why did you use equals to signs where you wrote x equals something equals y?
Well, so I defined it this way. So I want paths from x to y. And what I'm doing here is I'm defining v naught to be x and vm to be y.
Okay, that makes sense.
Does that make sense? Yeah.
Yeah.
So I mean, there's an implicit definition going on here. Okay. Now, what looks wrong with this picture?
There's a cycle.
Okay, what's the cycle?
It starts at x, goes say along pi1, and then goes to y, and then along pi2, and goes back to x.
Yeah, so it goes backwards along pi2, right? So observe that v naught, v1, all the way to vm, and then now you go backwards. So vm is equal to y, right? Which is equal to wl, and now you start going backwards. So this is equal to x. We'll write it like this. This is equal to x. This is a cycle. But I'm not done yet, actually, because remember, a cycle is a simple circuit, right? So this is a circuit. But I'm not done because it might not be simple. Does this always have to be simple? Here, let me help you a little bit with this. So you could be in a situation like this, where your two paths share some edges in the beginning, right? And then this doesn't really work. This is not a simple circuit. So this doesn't really solve the problem. Any ideas on what we should do?
Don't we know that it's simple since a graph has to be simple?
Sorry, so simple circuit means no edges are repeated in the whole circuit. Simple graph means there are no double edges, so they just have different meanings. So we don't know that the circuit has to be simple, right? This picture can arise in a simple graph. No edges repeated here. It's just that these pi1 and pi2 have an overlapping part.
We
Does
can
that answer your
try,
question?
yeah, we can try and start at a later point in pi 1 and pi 2, such that
Exactly. It's a great idea. So the general picture looks something like this, that these, these paths can branch out, then they can meet up again, then they can branch out again, then they can meet up again, and then they can eventually reach y, right? But as you said, maybe it's a better idea to start at the point where they branch out and then find the first point where they meet back up again. And then that thing is going to be a simple cycle. Now we have to write that into a proof. So let's do that. So here's how it's done formally. Well, you ignore the part where they share the same vertex, right? So let S be the first index, or let's say, let's maybe not the first, be the last index, the last time they're sharing. Well, okay, this is a little bit awkward. We don't really want last. Let's say, let S plus 1 be the first. Well, okay, let's think about how to phrase this actually. Yeah, let S be the first index after 0, or so starting with 0, such that they branch out after the S index. So such that V sub S plus 1, so that the next step in V does not equal W sub S plus 1. Right? So the two paths are called V and W. They're labeled by V1 and W1, right? So this is V0, V1, V2, et cetera, et cetera. But then there's also another path with W's. But W0 is equal to V0. So there is some first index at which they're not equal, because they're equal at index 0. So in this case, S is going to be equal to 2. So you find the first branching point. Okay, and now the intuition is you follow the paths until they meet up again. So again, how should we formalize that? Any thoughts?
We could maybe let I be the first index after S, such that V of I is equal to W of I for some, or sorry, W of J for some J.
Exactly. Yeah, you nailed it. So so for symmetry, let me call it T, because I have S and T. So let T be the first index after S, such that V of T. Now this is a little tricky. V of T may not be equal to W of T, because these two branches might have different lengths. So V of T is just equal to W of J for some J. So in this case, in this picture here, V of T is this vertex. So we're not doing anything very complicated. The challenge here in the context of this course is to figure out how to write this thing precisely. Okay, so we have these two indices, Vs and Vt. So this is Vs. And now we're in business, because none of the edges in pi 1 between Vs and Vt can occur in between Ws and Wj. because I chose P to be the first index at which they share a vertex. So now the key point is, so now the paths pi1 prime, which is just a subpath along Vs to Vt, and pi2 prime, this goes from Ws to Wj. They don't share any vertices except at the endpoints. Okay, so their endpoints are the same. Vs is equal to Ws, Vt is equal to Wj. Right? Because the way this is defined, this means Vs is equal to Ws. But now when I glue these things together, I'm actually going to get a simple path. And pi1 prime, pi2 prime do not have common vertices except at the endpoints. And now I'm happy, right? Now, if you look at pi1 prime followed, I mean, okay, so let's just write it out. Vs going to Vt. Now this Vt is equal to Wj. And now you go backwards. Wj minus 1 all the way up to Ws is a simple cycle. No repeated vertices, so no repeated edges. So G is not a tree. That's what we wanted to prove, right? Going all the way back to the contrapositive, right? We assumed that there were two different paths. We wanted to show G is not a tree. We succeeded. We constructed a simple cycle. So sorry, I'm still not done. I'm done with half of the proof. Okay, so as desired. So the challenge here really is writing and being careful, right? It's very easy to make this mistake. I have personally made this mistake many times. You say, oh, you have two different paths. You combine them together, you get a cycle. Yeah, you get a cycle, but you know, you don't get a simple cycle. And actually, there is one kind of loose end here. How do we know that we actually get a cycle when we do this? How do we know we don't just get a cycle of length 0? Anyone see in the proof where we know that pi1 prime and pi2 prime have to consist of at least one edge?
Is it because X and Y are distinct nodes?
X and Y are distinct, but you know, the bad situation that we're worried about here is what if pi1 was equal to pi2, right? Then if you do this argument, you don't get anything, right? So X and Y are distinct, but that's not quite the reason.
Someone
Any other
pointed
thought?
out in the chat that we chose T after S. And that is helpful because we know that now these have to be sort of separate points in pi1.
Exactly.
Pi1 is a simple path.
Exactly. So this after S, this means Vt is not equal to S. Okay. And the reason such an index exists, so really there's some implicit stuff going on here. The reason this exists is that eventually the two paths meet, right? So they have the same endpoint. So there has to be some T at which Vt equals Wj. So whenever you say let, you better be sure that that thing actually exists, right? And so the reason this exists because eventually the paths coalesce. V M equals WL. And again, why does this exist?
Because if it didn't, pi1 would equal pi2.
Yeah, exactly. This exists because the paths are different. Okay. So sometimes these things can be written implicitly, but if you want to be extremely sure, you just add a line saying this exists because of this reason. So as part of the challenge of graph theory, it's a little slippery because you don't often imagine all the scenarios. Anyway, we've completed this half of the proof. Any questions about this half of the proof? The basic idea is just this, but there's this annoying, you have to do a little bit of technicalities to make sure that it really works because of these overlapping.
Have we made a mistake at all with referring to paths by their vertices, since we haven't yet shown G is simple?
So why is it okay to refer to well, okay, so it's okay to refer to these paths by their vertices since they are simple. Okay. So that's okay.
Awesome.
And after we've cut off these parts, the paths we're looking at are also simple. So it's fine.
Thank you.
So this is a good point. So in the original definition of a path, I refer to it as a sequence of edges, right? And let me just add a remark. The remark is that a simple path. So I'm good. The most, verbose way to write a path is to write it as an alternating sequence of vertices and edges. Is uniquely determined by the vertices. Okay, there's no, if there are no repeated edges, then, I mean, it's actually, well, it's actually, I mean, in a simple graph, actually, a path is uniquely specified by the sequence of edges.
Wait, so if it doesn't hold when G isn't simple, do we have to show that G is simple before we can use this in our proof?
Yeah, so let me actually make this a little bit stronger. In a simple graph, there's something even stronger. In a simple graph, so in a simple graph, if I tell you two vertices, there's only one edge between them. So I don't ever have to specify the edges. So yeah, thank you for being careful. I'm using this implicitly here. Let's just assume all graphs are simple for this section. I don't want to, I mean, we get it for free because of what I said. If a tree is not a simple, a non-simple graph can never be a tree because a multiple edge is a cycle, right? So let's write this as a remark. I don't want to rewrite it in the proof. So a multi-graph, so a non-simple graph, so with a repeated edge, can never be a tree. Why? Well, because it contains this simple cycle. The repeated edge is in itself a simple cycle. Okay, good points. Any more comments on this? Okay, let's do the other side now. So the other side is to show that if every pair of distinct vertices is connected by a unique simple path, then the graph is a tree. And we'll again do it contrapositive is easier. Contrapositive is assume the graph is not a tree. So assume G is not a tree. There are two possibilities. One is it's not connected. So if G is not connected, there's some pair of vertices without a path, so it doesn't have a unique path. Okay, that's kind of a trivial case. The second more interesting case is that if G has a cycle. So if G has a simple cycle, so remember that's the definition of a tree. Acyclic means it doesn't, sorry, if G has a cycle is a simple circuit. Well, let's give it a name. So let's say assume G has a cycle. Has a cycle C. So let's draw a picture of the cycle. So a cycle is a simple circuit, so no repeated edges. And what I need to do is show that there's a pair of vertices that doesn't have a unique path. So G could have some other stuff going on too, by the way, right? It could, whatever. But it does have this simple cycle C. So how am I going to produce a pair of vertices with two paths from the cycle?
Choose any two vertices on C.
Could choose any two vertices. To make our lives even easier, let's just choose some two adjacent vertices, X and Y. Now, and let's say C is, this cycle here. Well, there are two different paths between X and Y. One is just the edge XY, and the other is you go around the cycle the other way. So that's it, right? So let XY be any edge in C. And now there are two distinct paths, right? There are two distinct simple paths. Between X and Y. One is just XY. And the other is the cycle minus the edge XY, interpreted in the obvious way. If you delete XY from the cycle, you get a path from X to Y. That completes the proof. Okay, so G is not a tree. So there are two paths, which is what we wanted to show. Okay, so now we have these two nice characterizations of trees. One is in terms of unique paths, and the other is it's a connected acyclic graph. So any questions or comments on this? Okay, so now we'll prove a couple more things about trees. So yeah, so next we'll prove that every connected graph has a spanning tree. Okay, so a spanning tree is a subgraph which is spanning, which is a tree. So definition, a spanning tree of a graph G is a subgraph. Is a spanning subgraph, which is a tree. Okay. And here's a theorem that will prove a graph G G is connected if and only if it contains a spanning tree. Okay, so this is connecting two different concepts. Connected is something about every pair having a path. And this is saying being connected is the same thing as having a certain special kind of subgraph, namely a spanning tree. So let's prove this. Let's prove the forward direction. The forward direction is really the more interesting one. To assume the graph is connected, and we're going to prove it contains a spanning tree. Any ideas on why this would be true?
Well, if it has a spanning tree, then within that tree, the tree has to be connected. So within that tree, we've always got a path between any 2 points, and that path is also going to exist in G.
Right. So what you're describing is the other direction of the proof.
Oh.
You're saying if the graph has a spanning tree, then it's connected. So since you've said it, let's just write it here. So assume T is a spanning tree of G, and now let X and Y be distinct vertices in G. Since T is spanning and T is connected, there's a unique path between X and Y and T, right? Here we're using our previous theorem, right? Or I mean, we don't even need the theorem. There is a path because T is connected. So let's just say it that. Let's just use the easier fact, right? So since T is connected, huh?
May I see the theorem again?
Yeah, so the theorem says that a graph is connected if and only if it contains a spanning tree. And so what Ben pointed out is the backward direction of the theorem. So if a graph has a spanning tree, then it's connected. So we're proving that. Assume G has a spanning tree. Let X and Y be distinct vertices in G. Since T is connected, there is a path pi from X to Y in T. And now we're using one fact about subgraphs, which is if you have a path in a subgraph, then all that path is also lies in the bigger graph, because all the edges in the subgraph are contained in the bigger graph. So now pi, so since pi is also a path in G, so, or you just say, but pi is also a path in G, since, since T is a subgraph of G. So that direction is easy. The more interesting direction is this. If the graph is connected, then it has to have a spanning tree. So anybody have any thoughts about why that would be true? Let's look at some examples. Let's look at our example G from before, right?
Something interesting in the chat.
Something interesting in the chat. Forward can be done with induction. Yeah, you are right. So that's the answer. Okay, so let's do it by induction. So the idea here, before doing the proof, let me explain the idea. The idea is if you give me a graph, if you give me a connected, so the graph is connected, right? If it doesn't have any cycles, I'm done. Otherwise, it has a cycle. So what do? I look at one of these cycles and I delete one of the edges. That doesn't change the connectivity because I can always go around. So this is a nice property of cycles. If you have a graph with a cycle and you delete any edge of that cycle, the graph remains connected. And then the idea is to use induction. So let's do that proof. So by induction. So assume the statement is true for all graphs. So okay, so let P of n, the formal P of n is a statement that if a graph with n edges is connected, then it contains a spanning tree. Okay, so now a base case is P of 1 is just this graph. This is true. There's only one graph. There's only one connected graph with one edge. Okay. Okay, inductive step. So assume P of k. And now let G be a graph with be a connected graph, right? So I want to prove that every connected graph with k plus 1 edges has a property. So let G plus 1, let G be a connected graph. With k plus 1 edges. Now there are two cases. If G is a cyclic, we're done. Right? If G doesn't have cycles, it's already a tree, so it contains a spanning tree. Since it's its own spanning tree. That's not that interesting. The interesting case is what if it's not connected? Otherwise, it has a cycle. So otherwise, let C be a cycle in G. So G has this picture where it has, it could have all kinds of other stuff going on, but it does contain this one cycle. Now I want to use induction. I want to turn this into a problem about a smaller graph. Now the key observation is if you delete any one of the edges on the cycle, you're not going to disconnect the graph. Okay. So let xy be any, or let's just say choose an edge, choose an arbitrary edge. Let's just be more specific. Let's choose an arbitrary edge xy in the cycle and let G prime be G minus this edge xy. So, okay, I guess this should be made clear that this means I'm deleting the edge, not the two vertices. Okay. Now, what are the important features of G prime? Well, one is it has at most k edges. Obviously, because I deleted one edge. But the more interesting thing is G prime is still connected. What's a formal, can anybody think of what the argument is to say that it's still connected? Connected means for every pair of vertices, there's a path in G prime. G prime also has the same vertex set as G, by the way.
Suppose for contradiction that G prime wasn't connected, then we've got some two vertices that don't have a path between them. We know they have a path between them in G because G is connected. And if the path passes through, if the path doesn't pass through the edge we deleted, then obviously it's going to be a path in G prime. If it passes through the edge we deleted, we can construct a new path by going the other way around the cycle. I'm not sure how to formally describe.
Okay, so I think you have the right idea, but that was a little bit maybe more complicated than it needed to be. Like you did some double negation and stuff. Anybody else have an idea how to express this?
Could we say that if we remove the edge xy and xy and x and the vertices x and y are part of a cycle, then we know that the degrees of x and y are at least 2. So we'd be reducing the degree by 1, which means there would probably still be a path to each of the vertices.
Well, that's not enough, right? Just the degree. Degree is just looking at what happens in one step. It's not enough to say, you know, it's not enough to really say the path could be long, right? So it doesn't imply that there's a path. Anybody else? I mean, okay, so the picture here is that there's a cycle, there's some x, y. And the key property of a cycle is when you delete this edge x, y, you get a path from x to y, pi. And now you have to imagine, to show that the graph is still connected, you have to consider some other pair of vertices in the graph. Let's call it S and T. And say if there was a path from S to T, then there's still a path from S to T after you delete xy. And why is that? Well, that's because you can replace every occurrence of xy by pi. So this is how you formalize it. So now if let's say A, B is a pair of distinct vertices in G prime, then there is a path from A to B in G prime obtained by taking a path from A to B in G and replacing every occurrence of xy by pi. Okay, let me move this down so I have more space to write. Or I mean, let me be more precise. Let me say for every pair of distinct vertices A and B, right? Because I want to make the quantifier extremely clear. So for every pair AB, of distinct vertices in G prime, there's a path from A to B in G prime. How do you get that? Well, it could have, so A, B could be sitting somewhere else, right? A and B could be like here. And they might originally have had a path through XY, but the point is I can reroute it through pi because of the cycle. Obtained by taking a path from A to B and G and replacing each occurrence. Well, there's only one occurrence because it's a simple path. Replacing any occurrence of XY. There may be no occurrences. Of XY by the cycle minus the edge XY, which is also a path from X to Y. Okay, so that's really the argument that you can reroute all paths that use XY. But now G prime is connected and has K edges, right? So since G prime is connected and has k edges, it must contain a spanning tree by induction. But now that tree is a spanning tree of G because I didn't change the vertex set. Spanning tree T. T is a spanning tree of G since G and G prime have the same vertices. That's it. That's the proof. Okay, so I'm being very detailed here since we're new to this. And later in life, you may be able to write these more succinctly, but this is, I think for now, this is a good level of detail. So the important features here, I mean, in this, so when I learned this stuff, it was quite challenging for me because it's a lot more prose than other proofs that we're used to writing, right? You're really describing something happening. And that's kind of all math is. It's just carefully describing things. Usually those things are numbers and we have very concise notation to do it, but in graph theory, you just have to use English. But you have these keywords, right? You have these special words like cycle, connected, adjacent, path, etc., which have very clear meanings. But they're quite intuitive. So any comments or questions on this proof? Okay, good. So we just proved the graph is connected if and only if it has a spanning tree. Now I was gonna do coloring, but there are only 20 minutes left. I could try to do it, or I could prove some more things about trees. Anybody have a preference? You can just enter it in the chat. Okay, is everybody okay? I'm not sure what that means. Trees, proof of about trees or coloring? Coloring trees. Okay, most people are saying trees. Yeah, let's do trees. Trees is a really important thing. Okay, I'm going to prove two more facts about trees that are used a lot wherever trees show up. So I'm going to prove two more theorems about trees. So if you look at these trees, so if you try to draw some trees, you'll notice that they always have a degree, at least 1 degree, 1 vertex. Right? You can never draw a tree where all the vertices have degree bigger than 1. So these are special and they're called leaves. With following the analogy with actual trees, I guess. So here's a definition. A degree 1 vertex of a graph is called a leaf. And here's a nice simple theorem about trees. Every tree has at least 1 leaf. Actually, let's just say 2. Every tree with at least 2 vertices has at least 2 leaves. Okay, let's see the proof. So first we're going to prove that every tree has at least 1 leaf. Well, okay, you know what? Let's just prove 1 leaf. The time is short. 1 leaf is enough for all the applications. Okay. So what's the proof? Well, any thoughts looking at these pictures? If I give you a tree, how are you going to find a leaf?
Can we do this by induction?
Yeah, well, it's a sort of induction. What kind of induction? What are you going to do induction on?
I was thinking we induce on the number of vertices.
It's kind of tricky. How, I mean, yeah,
Oh,
it doesn't, it turns out being kind of circular if you try to do that. It can be made to work, but it's very cumbersome. So it's a connected acyclic graph. So claim is a connected acyclic graph has to have a degree 1 vertex. Okay, let me explain the idea before the proof. The idea is actually quite nice. The idea is, well, you have a tree. So if you pick some vertex, x naught. Now you go to its neighbor, x1. Now you choose another neighbor that's not in the previous neighbors you looked at. And now you keep doing this until you're stuck. Now there are two ways you can get stuck. So one way is you found a leaf, in which case you're happy. The other way you can get stuck is if you reach the vertex, let's say xk, such that all the remaining edges coming out of it go back to somewhere in the cycle. Now, can that happen in a tree? No, because the tree doesn't have any cycles. So let's formalize this. So let x naught be an arbitrary. So let's call, gives us a name of the tree T. So this has at least two edges. So now let x1 be a vertex adjacent to x naught. And now I'm going to just inductively define a path. So inductively define a path x naught, x1, x2, dot, 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 where the next vertex, xi plus 1, is adjacent to xi and distinct from everything you saw before. You can do that, right? I mean, you can do that for a while until you can't do it. You can't do it anymore. Well, why does this process stop?
the graph is finite.
The graph is finite. Yeah. Every time you do this, you choose a new vertex. And so this process has to stop. So this process terminates or let me think about how to phrase it. So I actually wrote this in my notes. Yeah, this process terminates at some path, at some simple path. This process terminates at a simple path, x0, x1, all the way up to xk, such that one of two things happens, right? Either xk is a leaf, that's why I couldn't continue. So that either xk is a leaf, or I got stuck for some different reason, or xk is incident, or is adjacent, or how to put it, is adjacent only to previously visited vertices in the path. So in particular, it's adjacent to some xi, or xi is adjacent to xi for some I less than k, right? I mean, if it's not a leaf and it's not adjacent to any of the previous ones, you could keep going. But now this latter thing is impossible, right? The latter case is impossible, since then this xi plus 1 going all the way up to xk, xi would be a simple cycle in the tree. Or just be a cycle, sorry, cycles are always simple, it would be a cycle in T. That's it. So it's a kind of induction. It's an inductive definition of a path. You start somewhere, you just keep walking. You keep walking until you get stuck. And there are only two ways you can get stuck. One is it's like the games, snakes or whatever. I don't know if people still play this game, where you have a snake that it can't touch its own tail, right? That's kind of what's going on here. You keep doing that until you get stuck. And then, well, there's no cycle. So the only way you get stuck is that you hit a leaf. Where did I use that there are at least two vertices, by the way?
When you chose x1 as a vertex adjacent to x0?
Yeah, and I kind of had to choose x1 because in the inductive definition, here I'm talking about x1 through xi minus 1. And this wouldn't make sense if I was 0. So the base case of my inductive definition has to involve two vertices, x0 and x1. And that's why I needed two vertices. And indeed, this wouldn't work if there's one vertex, right? A one vertex tree is just a vertex with no edges. And it doesn't have a leaf. It doesn't have a degree 1 vertex. Okay. Now that we're going to use this to prove a last kind of very sort of, in my opinion, clarifying theorem about trees, which tells you how many edges they have to have. So here's the theorem. A tree on n vertices has n minus 1 edges. And this will now follow easily from our little fact that a tree has a leaf. So proof by induction. So let P of n be every tree on n vertices has n minus 1 edges. The base case P of 1 is true because the tree is just an isolated vertex with no edges. And the inductive step, so let T be a tree with k plus 1 edges. So there's some tree T here. Okay, I don't know. That's a tree, okay? Now, how am I going to do induction? To do induction, I need to find a smaller tree. So given a tree, what's a good way to find a smaller tree that's contained in that tree?
Let V be a leaf and consider T minus V.
Exactly. So the beauty of leaves is that when you delete a leaf, you get another tree. Okay? So when you delete a leaf, for every other pair of vertices, there's a unique path between those two vertices, right? And that cannot use any leaves because the leaf only has degree 1. So when you delete a leaf from a tree, you get another tree. Okay, so is the key step. So let X be a leaf of T, or let's give it a name. Let's call it V. And let T prime be the tree obtained by deleting V. Now T prime doesn't have any cycles because I didn't add any edges. So it's acyclic. I mean, it's a subgraph of T, but it's still connected. And here I have to use the unique path property, right? So if X, Y is a pair of vertices in T prime, distinct vertices, there is a path from X to Y in T, which doesn't use this vertex V. And so therefore this path also lies in T prime. Right, so T prime here is everything else. I mean, this is again kind of intuitively clear, but writing it formally is a little bit annoying. So this path lies in T prime. So T prime is connected. So now by the inductive hypothesis, it's acyclic and connected, right? So by induction, T prime has, so by the way, how many vertices does T prime have? It has K vertices. Sorry, it has, sorry, this shouldn't be edges, this should be vertices. So T prime has K vertices, so it has K minus 1 edges. But now T just has one more edge, right? Because I deleted a vertex of degree 1. T has one more edge. Since V is a leaf, so T prime has K edges as desired. Okay. So this leaf thing is extremely useful. Whenever you do prove anything about trees, this is what you do. You do induction by deleting a leaf. I mean, not 100% of the time, but most of the time. So trees are the perfect structure for strong induction or for structural induction. And the reason is that they have leaves. When you delete a leaf from a tree, you get another tree. So that's actually all I wanted to say about trees. So that's it for today. We'll do coloring next time. But any comments or questions about trees? Okay. Well, have a good break, everybody.
Thank you. You as well.
Thank you. Bye.
Thank you. You too.
Thank you. Have a good Thanksgiving.